Now we take another step into some special techniques for getting area under a curve. And in this case, we're going to go for area between two curves. So additional integration techniques, getting the area between two curves. And let's think about when might we need this? Well, we might have two separate functions, something like revenue and cost. When we get what might that area between the cost and the revenue equal? The cost is what we have to pay out from the revenue. We have to sort of subtract it off the revenue to get our profit. And that's exactly what we're going to do. So this is a very important business use of the integral for finding profit. Profit is not something you necessarily find directly. You really have two separate processes. You have a cost process and you have a revenue process. And the difference between those two is what will determine your profit. So let's look at the mathematics behind this, how we can go about finding the area between two curves. And remember, the area underneath the curve and the x-axis, that's just the integral. So when we are finding the area between the two curves, really the theory says as long as we take the one that's larger, in this case they're showing f of x is the larger function, or the y values are higher, at least in this area we're considering, so that we subtract the g of x function, which has lower y values. And when we do that, what we're effectively doing is getting the area between the curve. What we're going to need to do is make sure we graph the functions so we know which one's on top, which one's on bottom. And we're going to see when they switch, because they can, that happens, then we're going to have a separate integral with those limits. But we'll get there next. But the concept is you want to find the difference between two numbers. What do? We subtract. We want to find the area between two curves. What do? We subtract the two functions. And the integration will give us that area. And we need these limits going from A to B. That's important. And we'll see sometimes we're just given that, and sometimes we need to find that ourselves. Okay, so let's start this out. We're given an example here, one function, f of x, and the other function, g of x. We want the area between these functions between x equals -1 and 1. So the first thing we do is we graph it, and we find that let's see, now the functions are gone, so let's go back. F of x and g of x, so this is negative, so let's go to the next one. So the one with the negative, f of x, is on top, g of x is on bottom in the range that we're looking for. So all we need to do is find the integral of f of x minus g of x. Okay. And then we go from A to B. Okay, so -1 to 1 is what we're being told here on that interval. We take the f function, subtract the g function, and then integrate. Simple enough, right? So here's the f function, here's the g function. So then we're just going to simplify. The negative gets distributed through. So this is a negative x squared. This becomes a positive 3x and a positive 4. So when we combine these, we see a negative 3x and a positive 3x. That's going to cancel. We've got a +4 and a +4, so that's going to give us 8. And then we've got a minus x squared and a minus x squared, so that becomes -2x squared plus 8 dx. So you'll see that on the next page. We actually combine the functions, combining like terms. So that's what we get, and it's much simplified now. Now we just integrate each of these terms, right? So when we integrate 8, we get 8x. We integrate -2x squared. Remember, we add 1 to the exponent. So we've got our negative 2x to the third power and divide by the new exponent. And then what we're going to do is we're going to take the negative 1 to 1. And remember, this is sort of like a new function. It is the two functions subtracted. I went a little bit fast here. So the way they go about this is they plug in 1 for x. So you get 8 times 1 minus 2/3, 1 square cubed. It'll be the same thing either way, right? And then you subtract off what you get when you plug in the negative 1. And be careful to always put this parentheses because that negative has to distribute to all the terms. So 8 times negative 1 minus 2/3 times negative 1 to the third. So that gives us 8 minus 2/3. This negative will distribute through. That's going to become negative 8 with another negative becomes a plus 8. And then a minus distributes here, but let's do the third power here. Negative 1 to the third power is negative 1. Negative times negative is positive, but then when this distributes through, we get another positive. Really? That's positive. Wait a minute. Negative and negative is positive. One more negative. We don't get a positive. Negative is positive. A negative times a positive is negative. Okay, because I can see what the answer is, so I knew we had to have a third left over, right? So that's 2/3. So 8 plus 8 is 16. Negative and negative 2/3 gives us a negative 4/3. You've got to get a common denominator, which is thirds. So multiply 3 over 3. And 16 times 3, 18 carry the 1, 3, that's 48 over 3 minus 4/3. That's how they got the 44/3. Okay. So really, in a sense, the new step was previous as we were given two functions. We had to figure out which one's on top, which on the bottom, subtract the two, integrate. So there was not a lot of new stuff here, but just that one part. We're going to look at a couple of complications that can occur and things we need to look at when we're comparing the two functions we're given. Okay, so we'll take a look at a few problems, but other than that, notice there's nothing new about the integration part. We're just integrating, and we're doing a definite integral, so we don't need the constant. Okay, so here's what we need to do. One of the first things we need to do is we need to graph both of the functions we're given and find where they intersect. Okay, we also look when we're graphing them, we look at the limits that if we were given limits, we look what those are, because then the intersections might not be important. Just like this last one, we really didn't care about the intersections, right? Because as we go back here, to go back a little bit more, we saw that where the intersections were really didn't matter because the area where we're interested in was internal to any of the intersections. We're going to take a stretch on this and see that if our interval of interest was larger, we would actually have to know where those intersections are. Okay, we'll go through this again. So we want to find those intersections, and sometimes that's what determines the interval. Sometimes we're given the interval, and sometimes we've got to break them up into multiple intervals. We'll show you with an example. Then we determine the area of each region that we find, and we may get more than one. We'll show you an example of that. The difference of the larger and the smaller function in terms of their y values, which one's on top versus the bottom. And we may have to add those areas together if there is more than one. This last one, there was only one area, right? It's continuous, boom, we're done. But we're going to see some where there's actually two areas. Here's one, two areas, right? And notice one of the functions, f of x here, x square root of x, starts out as the larger function. It's on top, the blue. But at the intersection point, it now switches. The f of x function is on top. So on this one, we would actually need to set this up as the integral from 0 to 1. And which one needs to be on top? Well, they call them both f of x. One's blue, one's, I should have checked that. Let's call this g of x. You got to have two different names. So g of x is bigger. For this area, we subtract f of x. And notice we're just going from 0 to 1, from 0 to 1 right here. So that's going to give us area 1. And of course, there's always this dx. Now, when we go for area 2, we're going to go, the limits go from 1 to 2. So I'm going to give us a little bit of room here. We're going from 1 to 2. But now, this one, which one is this one? This one is actually the f of x. This is x squared, right? We're switching, f of x goes first. And then we subtract g of x. And then when we're done, we add these two together because this is a1, this is a2. Okay, so we actually have to do the integration twice. They should be very similar because they're the same functions, but it's the order that we're subtracting them in. But so that will make a difference. It will make a difference. Okay, so we won't do it with this one. I've got a couple special ones lined up for us. Okay, this one that we saw before, since we saw the first graph, right? F of x is this function, g of x is this function. And notice, remember, we did this from -1 to 1, and we didn't have to worry about the intersections. What we're going to do now is, notice we're being asked to use different endpoints, different limits of integration. So how is that going to affect us? Well, we're going from -2. It looks like this is going to be an intersection point, which we will make sure, we'll check it out. It is, but we'll just make sure. I'll show you how to do that with the calculator. And then we've got to find this one, which it looks like it's at 2, and it ends up being at 2. So what we're going to do is we're going to break this up into two regions. We're going to go from -2 to 2, and then 2 to 3. But we don't know that quite yet until we actually verify that. So let's do that. Let's verify that with the graphing calculator. So where is it? It's right here. Oh, it's over here. So first, let me restart it. Okay. TI, I think is what it's called. Yeah, Smart View. And again, this is a, you get a 90-day trial, and I think I've got 7 days left, and then I'm going to have to pay for it, but I'll do that. I've had it before. I think I've told you that. Yeah, 7 days left. Okay. So what we're going to do, come on, behave yourself, right? We put these in, and I'm going to, let me clear this out so that you get to see step by step. So the first thing we're going to do is we're going to put f of x into one of these. And I'll show you, you don't have to re-enter them too many times. We can do all of this with the technology. Okay, so we need to put in -x². And at this time, it really doesn't matter which one you put first or second, because you'll see that. 3x, we're still there, +4. Okay. So make sure we get it in there correctly. And then the second one is x². over minus 3x minus 4. Okay. Then what we're going to do is we're going to go to the graph. I'm going to do a zoom standard, and it gives us a pretty good view. Sometimes that's something we need to do. One of the things we want to do is verify these two intersection points. Okay, and we see that the first one we draw, that we graph the f of x, which is blue, as a negative. It is above the g of x function for most of the trick, but then they switch once we get past this intersection. And we can see 1, 2, it looks like it's going to be at 2. We're going to 3. We're probably going to need to switch it. So, okay, so intersections. Second, calc. We want to find where the intersections are. Now you could do that by setting the functions equal to each other and solving for x. That would work as well, but this way works as well. I mean, we really have to look at the graph, right? Let's move. We want to see this one. And what I'm interested in is that when x equals -2, that's an intersection point. So when we're looking at the left-hand side here, that boundary is going to go right through that intersection. So we're going to be getting this direction forward. Okay. Okay. So to get the second intersection, I ask for second calc again, number 5, and I just need to make sure I walk my little spider guy closer, which it is. Enter and enter, and I get that the intersection is at +2. Okay, so what this tells me is I'm going to need to go back, get back there, and this guy, I forget, I have to reset and say always in front. So now I'm going to have what I can see here. Okay, there we go. This should hopefully work. I want the integral from -2 to +2. And what do we want for that one? We want f of x on top. And then we want to subtract g of x. So that'll be one thing we're going to look. That'll get us from -2 to 2. And then after -2, we look. Well, we go to 3. We don't have another intersection. We don't have to worry about that. So it's kind of going to be open-ended. We're going to go with an integral from 2 to 3. And in this one, we're going to want g of x on top. And then we'll subtract off the f of x dx. Now we could do this as they did last time, with putting the two functions there, subtracting off, combining like terms, doing it. It's not that difficult. We saw we could do it. It was like we got an x squared and an x, right? So we get an x cubed. We could do that. But what I'm going to do is show you a slightly different way, because we'll do some others that are like that. I'm going to show you how you can do that with the graphing calculator itself. Okay, so what we're going to do is we're going to go back to y equals. And what I'm going to do is, instead of having to retype these, which I could, I'll show you this method. We're going to, and I think I showed you this earlier in the semester, but we're going to hit the VARS key. What we're going to put in here is y1 minus y2. Okay, the way we go about doing that, we hit VARS, we go over to y-vars, and then we hit enter. And that gives us the functions, which are y1, 2, 3. We want to put y1 first. We're going to subtract off vars, y-vars, well, vars for variable. I always say, I don't know, it sounds like, I think of a pirate saying variable, vars. I don't know why the pirate hits, but it just does. Okay, so function, you know, the parrot on my shoulder, that would get you to remember it, right? VARS, hey, VARS. So this is y1 minus y2. Now, if I go to the graph, I'm going to get 3 different graphs, which I guess is okay, but I like calmness, So I'm going to turn off these two graphs. So I come to the equal sign, and if I hit enter, these ones will not graph. I can't delete them. They need to be here so that I can see the combined graph, y1 minus y2. So I'm going to go to graph. y1 minus y2 is now graph. And watch what happens. I'm going to go second calc, use my integration tool, 7. My lower limit is -2. And watch that, that's right there. It's actually one of the x-intercepts now, because when we subtracted them, that's the place where they intersect. They equal 0, right? So it was up here, but now it's down there on the x-axis. Kind of cool how math ends up working. And then our upper limit is 2. And watch this. 2 is right there. It's also an x-intercept, because when you subtract the 2 where they intersect, you get 0. And so now this first area is 21.333. I gotta train this thing to work a little differently. Okay, so now I've got the pencil. 21. Is that negative? No, it's not. 21.333. Which what you're going to do is you're going to remember that that is decimal code for 1/3. It's 21 and 1/3, which is plus 1/3. We're going to combine it with the other one. Okay, so now to get the other one, we come here, y equals. If you want, you could delete this and then put the new one in. I'm just going to turn it off just so that it's still there, and put a new one in. This one I'm going to do y2 minus y1. That will get us the next region that we're looking for. So again, we go to the VARS, y-vars, function, and then we want y2 to be first. And then we're going to subtract VARS, y-vars, function, and y1. Okay, and so that's kind of the heart. You gotta just keep keep things on track. In fact, maybe instead of f of x and g of x, we could have labeled this y1 and y2. Okay, we're going to graph it. Now notice at y equals 2, that's where the intersection was. That's a x-intercept of this one. We're going to get the area between 2 and 3, which is actually going to be positive value now. And so we do that with second calc number 7. And we want our lower limit to be positive 2, our upper limit to be positive 3. Boom, and we see it. You see that area, 4.6667. Okay, 4.666 repeating 7. And again, this is code for 2/3. So what we have is 4 and 2/3. And when we say and, it really means 4 plus 2/3. This means 21 plus 1/3. And remember when we did this earlier with their by hand, that's the numbers we ended up with, right? Something like that. Of course, it was a little different. And we want to add these two together. So what we can do is 21 plus 4 is 25. 1/3. And again, we don't have to do any subtractions. I'll cut 1/3 plus 2/3. So we got 26 as our answer. Okay. So notice what we ended up doing is we got the area from this intersection all the way to here. Here we go. So we're getting all of this, and then this shoots up like this. This went down like this. So we actually got the area between this area up to 3. And so, this was the 21.33, and this ended up being 4.667. We add those together, and that's the area between the curve. Okay. So let's keep moving forward, and we'll see this one. This one will be a little more simpler. We're going to do the same thing. We want the area between e of x and 3, y equals 3, g of x equals 3. and the y-axis. And here you'll see why we throw in the y-axis. So we're going to come back to our calculator. We can now remove all of these previous things that we did. You could leave the y1, y2 because that might be helpful. Actually, you could just leave it there, turn them on and off. I should have done that, but I wasn't thinking. So the first one, we have e of x. So we put that in, second e to the x, and then the second function will be 3. So now we want to graph it. Okay, and we want it from between the y-axis, which is this one here. And the reason they do is because, you know, they could have said like between -1. What they're really saying is x equals 0. Okay, that's what the y-axis is x equals 0 until they intersect. Okay, between these two curves and the intersection. Because you get over here, that would open it up forever. So we need to find the point of intersection. Okay, and when they're saying the y-axis, what they're really referring to here is, what they're really saying is that one boundary is x equals 0. The other boundary we're going to find out here. Well, we could use the intersection, but remember in this case, because I did this and I tried it with the WebAssign, but it wouldn't give me the right answer. It wouldn't give me the credit for that answer because it wants the exact answer. So this is one of the reasons why I did this one is to show you. The point of intersection is where these two functions equal each other. So the point of intersection is e to the x equals 3. Now, since we haven't been doing, I mean, we've got algebra all throughout this, but we've been focusing on the calculus part, I want to remind you about how to solve this kind of equation from algebra. Because you need to, because the technical side isn't going. So we take the natural log of both sides, right? Natural log, natural log. When you take the natural log of e to the x, remember these are inverses of each other. The answer on this side is just x. X equals natural log of 3. That is the number we want to use. Now it is a decimal value and such. You could plug it in, you can get the approximate value, but to get the exact value, we actually need to use this limit as being the natural log of 3. Okay, so what we have, we could go to the technology, I could show you how to do that, but that's not going to get you the correct answer in WebAssign. This will. We're going to go from 0, which is the y-axis, until natural log of 3. Natural log of 3 is just a number. And let me just plug it in here to show you. Natural log, oops, well, good, it worked that way. Natural log of 3 is 1.09861, so forth, right? We're going to come back here. Watch what happens. 1.09, just remember what it was. We'll come back to it. Number 5, we're going to actually find the intersection. So the first curve, we're on the first curve, hit enter. Second curve, hit enter. And then for our guess, we hit enter. And it finds the intersection at 1.0986123. 1.0986123 if you rounded it, okay? So that is the intersection point, natural log of 3. And we saw that actually 3, right, y equals 3 is above, so we just put the function as 3 minus e to the x dx. Okay, we integrate, so the integral of 3, remember, just becomes 3x, because if you take the derivative of 3x, you get 3. The integral of negative e to the x is negative e to the x. Simple. Not bad. Not that it's easy, because you have to know these things. You have to you know, memorized, internalized, simplified. Okay. So now we want to go from 0 to natural log of 3. So remember the way we do that, the top limit goes in first. So this is 3 natural log of 3 minus e to the natural log of 3, and this will be a nice pretty number, right? It'll just be 3. And then we subtract off, put the parentheses, what we get when we plug in 0. So 3 times 0, that's going to be 0, minus e to the 0. So what do we end up with? We have 3 natural log of 3 minus, notice this is just going to be 3 e to the natural log of 3. They sort of cancel, giving us 3. And what happens here? 3 times 0 is 0, so that's gone. E to the 0 is 1, so you get a minus on this. A minus and a minus make a plus 1. So we get all that right? I think we did. And so our final answer, 3 natural log of 3 minus 2. That's it. And again, you could plug in this number and get a decimal approximation. But one of the things you can do is you can always do that whenever the question in WebAssign says, round to 2, 3 decimal places. That's asking for an approximation. If it doesn't say that, if it doesn't tell you to round to so many decimal places, or doesn't use the word approximation, then you need to give it the exact answer. This is the exact answer. Okay, so that's that one. We don't have too much further to go. I just wanted to work through these examples together, and they will set you up. We've got 6 questions for you to work through in WebAssign, and this will give you a good start. And there's a couple in there that just follow this technique here, and you'll be just fine. So we've got a business proposition, a business operation here, and we were told that we've got daily revenue, which is given here, and daily cost, which is given here, and that these that where the variable t is equal to the number of days, and t goes between 0 and 7. Okay, so depending upon which day of the week, so this would give us a week, from 7 would give us the weekly revenue, or actually 7, if we plugged in 7, it gives us the revenue on that day. So here's the thing, to find the area between the graphs. So what we're finding is the accumulation from the start of the week to the end of the week, the accumulation of the area between the revenue function and the cost function. What is it we're getting? That's a good one. That's an important one. Okay, so we're going to do, let me move this over here. So we're going to come and graph this. So we've got 50 minus 70t. Oops, 50. Go back up to R1. 50 plus 70x. So these are just linear functions. They probably are not too difficult to work with. If you were to subtract them, if you were to do these ones by hand, that's perfectly fine. But what we always want to do is verify. We want to see the graph so we can tell for certain which one's on top. You might say, yeah, revenue hopefully is going to be on top of cost, but doesn't always happen. So we don't want to make the assumption. We can see, yeah, this starts above, right? X-intercepts or Y-intercept 50 over 25. It's increasing faster, so we can be pretty doggone sure, but we get this weird graph. And why? Because Y-intercept 50, 25. So what we need to do is set our window. That negative 10's fine. We're starting at 50 and we're going up. We're 25 and going up. Let's go for 1,000. Oh wait, that's x. X is how far? X goes from 0. Let's change this. Remember when we're dealing x. X goes from 0 to 7. Okay, so we'll go 0 to 7. You could go a little bit bigger if you wanted, but that's it. Y needs to get big. because as we plug in 7 here, this is going to be a bigger number. It's actually 1,000 might be a little overkill, but 500 might be enough. But let's just go this route. There we go. We can see it. And what we see is that the R of t, the first function, is always above the cost function. It's a good business proposition, and we can see with sort of volume production, our revenue is increasing more than our costs are, which is good for a business as well. We could produce over these 7 days, so the longer we stay open, the more we're going to get in there. So now we want to get this area between the curves. How can we get that? Well, since we know R of t is above, we can simply come down here. We do our VARS, y-vars function, and we do want y1 minus VARS, y-vars function, and y2. So y1 minus y2. We're going to go from 0 to 7. So we go to the graph. Oh, well, let me just show you what we can do if we haven't turned these off, right? But we know we want to deal with the black function. Now, if you don't have a color calculator, you definitely want to turn them off because it's hard to tell which one you want. But let's just see. Second calc, let's do number 7. Now notice it's on this function. We don't want that function. So if we arrow down, we don't want that function. Let's arrow again. So we kind of toggle between the functions. I just wanted to show you this in case you want to do it this way, because we can. It's now going to give us the area under this graph, which is the one we want. Again, preferable, just turn the other ones off and it won't even bother you. But the lower limit is 0. The upper limit is 7. And see, when we get done, it fills it in for us, so we're okay. It's 1,277.5. Since it's it's dollars, that's what we have. Okay, $1,277.5. That's the area between the curve. And what's the area between what happens when we take the revenue minus the cost? We get the profit. And remember, this is accumulated. This is total. And that's why I like looking at this. I can look at this and I can say, that is total profit, not just an average or anything. It's total profit. When we're getting an integral, we're getting a whole area, not just a single number. We've got to remember that. When we're using the derivative, oftentimes we wanted a derivative at a point, so we, that tangent line at a point. But when we're talking the integral, we're talking about accumulated, we're talking area, we're talking about what's happening over time. And that's what we get. Let's see if we got any other surprises for ourselves. That's it. Those will get you started on the homework. Give it a try. They're slightly different, so there's enough to get you through and do some problem solving. Remember, we always have the class sessions through Zoom where you can ask the questions you need or have. Let's see. Let me come to my my office in the sky. I don't know. I think I'm in New York, but maybe I'm Chicago. Maybe some of you know where I'm at. I thought it was a cool picture, so I always wanted a corner office on like the 57th floor. So since I don't have one, I made one. Anyway, stay safe. Keep moving forward. We're close. 3 more sections after this: 14.3, 4, and 5. More techniques on integration. We're going, and as we do each one, we're going to kind of keep building up what we've already learned. We're going to become stronger and more knowledgeable. We're going to remember these things. We're going to back and review them. We're going to have over a week and a half to review, almost 2 full weeks, before we need to take that final, that last test. And remember, the goal is we work hard, we work smart, we work consistently, and all of this is going to make sense for us. Remember, we're just really adding 1 to the exponent and dividing by it. We've got the 2 other special integrations that we're doing with e to the x and natural log. We'll remember those, and then we're going to remember all these different techniques we've been learning, because this is all we're going to focus on until we finish this course. We're going to do it together. We're all going to make it. We've got 93 students left. I want to see 93 students successfully passing this course. I won't accept anything less. Let's make it happen. Let's keep going. And so that then you can take either your summer or your fall, you're moving forward in your program on to 211, and you're just going to do wonderful things there. Thanks. Be well. Talk to you later.